Check the mic and make sure it sound right, boys.
Hey everyone, and thanks for tuning in again. In today's video, we'll be starting off with correlations, and this could be for two variables. It could also be for multiple variables, creating a correlation matrix. After correlations, we'll be looking at how to estimate a simple linear regression, which is a regression with one predictor, as well as a multiple regression. And for our example, we'll be looking at two predictors. For each of these regression analyses, I'll be going over how to interpret the results and be providing sample write-ups. So to begin, let's go ahead and open up our SPSS dataset, which will by default open up SPSS. We're switching over this time from the regdata1 dataset to the regdata2 dataset, which I've uploaded online. So if you just go ahead and find the regdata2 dataset on your computer, you could double click it and that'll open up SPSS and the dataset. So let's go ahead and get started. Okay, so what you should have now is the regdata2 dataset open, and that by default opens up SPSS as well. So here in data view, we could just go ahead and make sure our data have read in correctly, and it looks like it has. So we have Y, and then we have X1 through X5. Very similar to regdata1, but it is slightly a different data set. And then going into variable view, we just want to make sure that we have the appropriate variable names, and then that they're the appropriate scales of measure. So these are continuous variables, so they're appropriately set to scale. So we're good there. Okay. So what we'll start with are correlations. So if we go to Analyze, we can go down to Correlate, and then we want to choose Bivariate. Now we can choose the variables that we want to look at. And to start, we'll just do a simple correlation between X1 and Y. We'll click on Options, and we'll request our means and standard deviations, just in case we don't have those already. Click Continue, and then that's all that we'll have to specify out of these options here. We want to make sure that Pearson is checked. We want Pearson correlations. We want two-tailed significance tests, and we want significant correlations flagged, and they'll be flagged with an asterisk. Okay, so that's good. You can click OK. It will switch to our output window here, and as you can see, we have our descriptives. So we have our means and our standard deviation. So Y has a mean of about 49 with a standard deviation at around 10, and then X1 has a mean at around 10 with a standard deviation at about 3. And then here we have our correlation. So our correlation is here in the row Pearson correlation. It's 0.24, and the asterisks indicate that it is significant. The p-value is the significance value is 0.003, so this is less than 0.05, and then we also get our sample size here of 150. All right, so let's go ahead and compute correlations for the entire data set. So same thing, we'll go to Correlate, Bivariate, and now we'll just go ahead and select all of these. So you can hold Shift and click up to X5. That will highlight the rest of the variables, and then we'll just put them in the variables box. Again, let's check our options, and means and standard deviations is still checked, so that's good. We don't have to worry about missing values. And then Pearson, two-tailed, flag significant correlations, that all looks good. So let's just go ahead and press OK. Okay, so here we get our means and standard deviations again, but now we have them for X2 through X5 in addition to Y and X1. And then here we have our correlation matrix. So on the diagonal right here, you can see that everything is 1 because everything on the diagonal is each variable correlated with itself. So you have Y correlated with Y, and of course that's 1. X1 correlated with X1, that's 1, and so on and so forth for the rest of the variables. Now on either side of this diagonal, so we have the upper triangle and we have the lower triangle, and these are just reflections of each other, so you don't have to look at the whole correlation matrix. You can choose to just look at either the lower triangle or the upper triangle. And by reflected, what I mean is, so if you look at the correlation between X1 and let's say X3, which is right here, That's negative 0.016. But you can find that reflected on the other side too. So here, look at x3 and x1. So negative 0.016, same correlation, same variables. So again, you only have to look at the upper triangle or the lower triangle, and you don't have to look at both. All right, so similarly to the single correlation, let's say we want to look at y and x5. So here we have the correlation, which is 0.272, and the asterisks indicate that it's significant. The significance value is less than 0.001, so that's less than 0.05, and so that's statistically significant. And then we get our n here, which is 150. Okay, so that's it for correlations. What we'll go ahead and move on to now is estimating our simple linear regression, or a regression with one predictor. So what I'll do is I'll go to Analyze, Regression, and then Linear. I want to predict y using x1, and remember we're only looking at one predictor here. And then I'll go ahead and click on Statistics and make sure that I have the things that I want. So I want my estimates, I want my model fit, R-squared change. We don't need that yet, but you'll see that we'll use this later on when we look at hierarchical regression. You can request descriptives if you don't already have those. And other than that, that's all that we're going to look at. You can request plots if you want. You could save certain things if you need to. For options, we're not dealing with any missing data, so we don't really have to worry about that. And that's all that we have to specify before actually estimating our regression here. Okay. And then here you see that it says block 1 of 1. Again, this will make more sense once we get into hierarchical regression, but right now this doesn't really make a difference. So we can just go ahead and estimate our regression here. Okay. Again, this is the thing that I said that doesn't really matter for now, but it will matter later when we get into hierarchical regression. So the variables that we've entered, just x1 for now. And then here we get a model summary, and then we have our R, our squared multiple correlation, our R squared, our adjusted R squared, and the standard error. So most importantly, we're going to focus on the R squared. That's the variation in Y that's accounted for by the model, and in this case, the model is just x1. So about 6% of the variation is accounted for in Y. And then adjusted R squared, to put it simply, you just want there to be a small difference between R squared and adjusted R squared. And what that tells you is that the predictors in your model are contributing a fair amount of prediction to the model for predicting Y. Okay. Here we have our ANOVA table, so we have all of our sums of squares for regression and residual. We have our degrees of freedom, and then we can use those to compute our mean squares here, and then we have our F. So this is the F statistic for the model, and it's significant, indicating that our model significantly predicts Y. And again, our model is simply just x1. Okay. And then that will tell us the same information as for the test for the coefficients. So we have our coefficients here. Our intercept is at 41.24, so that's the value of y when x is 0. But what we're really interested in is the slope here. So the slope for x1 is 0.797. This is the standard error, and then SPSS also gives us the standardized coefficient by default. And so as you can see, the significance values here are identical, and that's because we only have one predictor. So this predictor, x1, is significant according to the t-test as well. The t-test for the coefficient. So again, just to reiterate, the F statistic here in the ANOVA table is the omnibus test for the model. It's testing whether the model offers significant prediction of y. And then the t-test here for the coefficient is testing the coefficient alone. So does x1 significantly predict y? But in the case of a simple linear regression with one predictor, the results are the same. Okay. We're going to go ahead and move on to the multiple regression where we look at two predictors. So we go to analyze again, regression, and then back to linear. And then here I'm going to go ahead and add x2. So now we have y as the dependent, x1 and x2 as the independent variables. All the same options, so we don't have to change anything, and then we can just go ahead and press OK. Okay, so here the variables entered, x1 and x2, our dependent variable is y. Here's our r squared, so it's changed. It's now 0.139, so about 14% of the variation in y is accounted for by the model. Again, adjusted r squared is not too different, so that's okay. That looks good, nothing to worry about there. And then again, we have our ANOVA table, sum of squares regression, sum of squares residual, the corresponding degrees of freedom, 2 and 47, and then we have our mean squares, which we use to compute our F value, which is, again, significant. So the model as a whole, with x1 and x2, contribute significant prediction of the criterion y. And then looking at the individual coefficients, we have the slope here for x1, which is 0.715, its standard error, and the standardized coefficient. And according to the t-test of this single predictor, it is less than 0.05. So x1 significantly predicts x1 significantly predicts y when we hold x2 constant. And similarly, x2 is, the coefficient is 0.895. Here's its standard error, and then the standardized coefficient. And again, according to the t-test, it's significant, it's less than 0.05, and so holding x1 constant, x2 is a significant predictor of y. Alright, so I'm going to go ahead and switch over to how we interpret our simple linear regression and multiple regression. And I've uploaded these write-ups online. And so putting everything together and drawing from the numbers in our ANOVA table, as well as the information on the coefficients, this would be what a write-up would look like for the simple linear regression. So a simple linear regression was conducted to test the linear relationship between y and x1. The results of the analysis suggest that y is significantly predicted by x1. And then here is what we call a statistical sentence. And we have the test, which is an F. That's the first part. And then inside are the degrees of freedom. So we have degrees of freedom regression and degrees of freedom residual. So 1 and 48. And then equals, this is the F statistic. And then we just report that P was less than 0.05. And so going back to our SPSS output, you can find that information here in the ANOVA table. So on 1 and 48 degrees of freedom, here's the F statistic, and it's less than 0.05. Okay. And then so here's our R squared value, so approximately 6% of the variance in y is explained by x1. And then to interpret the coefficient, for every 1 unit increase in x1, y is expected to increase by 0.80 units. And then again, we have another statistical sentence here. It's a t, and then the degrees of freedom are 148. And the degrees of freedom that go here are always going to be the residual degrees of freedom that go here for the F. So on 148 degrees of freedom, the t statistic is 3.02, and that's less than 0.05 as well. And going back to our output, you can see that here. So using the residual degrees of freedom, which is 148, our t statistic is 3.023, and that is less than 0.05. And so for every 1 unit increase in x, y is expected to increase 0.797 units. Okay. And then below here, I have the same interpretation, but using the standardized coefficients. And again, we draw those standardized coefficients, or for this example, the one standardized coefficient from this column here. So it's 0.241. And the way we interpret that is for every standard deviation increase in x1, y is expected to increase by 0.24 standard deviations. And that is the only part that changes from the raw coefficients to the standardized coefficients. Now moving on to the multiple regression here, the write-up will sound like this. Multiple linear regression was conducted to test if x1 and x2 significantly predict y. The results of the analysis suggest that the regression model significantly predicts y. And then here, again, we have our statistical sentence for the omnibus test. So the f on 2 and 147 degrees of freedom is 11.84, and the p-value is less than 0.05. Going back to our SPSS output, we find that here, 2 and 147 degrees of freedom, f statistic is 11.840, and it's less than 0.05. Okay, the model accounts for approximately 14% of the variance in y, that's our r squared. And then going to the coefficients one by one, x1 significantly predicts y over and above the effect of x2, so we're holding x2 constant. And then we have our statistical sentence here for that coefficient. So on 147 degrees of freedom, the t statistic is 2.82, and that's less than 0.05. Remember, that's the same as here. On 147 degrees of freedom, the t is 2.817, less than 0.05. Okay. And then for the second coefficient, x2 significantly predicts y over and above the effect of x1. Again, the t statistic is on 147 degrees of freedom, it's 3.71, and it's less than 0.05. And then to interpret the coefficients themselves, I skipped over the one right here. So holding x2 constant, y is expected to increase 0.72 units for every unit increase in x1. And then similarly, holding x1 constant, y is expected to increase 0.89 units for every unit increase in x2. And where we get those coefficients are here, the unstandardized coefficients, so 0.715 and 0.895. All right, and then looking here, we have our standardized coefficients, 0.216 and 0.285. And that is the only thing that changes, what I have highlighted here, when we're going from the interpretation with the raw coefficients to the interpretation with the standardized coefficients. So holding x2 constant, y is expected to increase 0.22 standard deviations instead of units for every standard deviation increase in x1. And then similarly for x2, holding x1 constant, y is expected to increase 0.29 standard deviations for every standard deviation increase in x2. And that is the interpretation for the standardized coefficients. So again, we've computed correlations for two variables and for multiple variables, creating a correlation matrix. We've estimated our one predictor regression and interpreted the results for both the raw and standardized coefficients, as well as estimating our multiple linear regression with two predictors for the raw and standardized coefficients. And with that, that concludes our video today on correlations and simple and multiple linear regression in SPSS.